he merely denied that heat is a form of energy. He believed that heat did work by falling down a temperature gradient, much as water does work by falling down a gradient of height. Carnot ruled out a spontaneous passage of heat from a cold body to a hot body on the same ground that he ruled out the spontaneous ascent of water up a hill. Both would be violations of energy conservation, producing work out of nothing. Ironically then, for Carnot, the impossibility of heat flowing from a colder to a hotter body is not an original and independent law, but rather a routine consequence of the law of energy conservation. Because he misunderstood the nature of heat, he was unable to recognize the significance of what he had in fact found, the second law of thermodynamics. The theorem proved by Carnot has important consequences, both theoretical and practical. Practically, it means that a heat engine operating between two fixed temperatures can be made more efficient only by making its operations more perfectly reversible. Changing the working substance, say from steam to air or alcohol, will not raise the maximum rate at which work can be derived from heat. Theoretically, Carnot's theorem means that in a perfectly reversible heat engine, the work produced per unit of heat absorbed depends only on the temperatures of the furnace and the refrigerator. Carnot himself never found the formula expressing that dependence, so he could not write down an expression for the efficiency of a reversible heat engine. That was one of the great tasks that he left to his immediate successors, Lord Kelvin and Rudolf Clausius. More importantly, Carnot's work led within a generation to the discovery of entropy and the precise mathematical statement of the second law of thermodynamics. For the rest of the 19th century, despite his embrace of the ill-starred caloric theory, Carnot's idea of the perfect heat engine as a reversible cyclic process operating between two temperatures became the indispensable vehicle for all serious progress in thermodynamics. It captured the imagination of all the great scientists who came across Carnot's work, and it led more or less directly to the completion of classical thermodynamics in the 1850s and 60s. Let us see very briefly how things turned out. For a generation after it appeared in 1824, Carnot's book was almost entirely neglected. It was then rediscovered by Kelvin and Clausius around 1850. In the meantime, the investigations of James Joule had undermined the authority of the caloric theory of heat. Kelvin himself, however, still believed in the conservation of heat when he embraced Carnot's ideas in 1848, and it seemed to him highly doubtful that Carnot's treatment of the heat engine could survive if one abandoned the axiom that heat is indestructible. It was instead Clausius, in 1850, who first saw clearly that Carnot's main ideas could be salvaged even if the caloric theory of heat was discarded in favor of the mechanical theory. Clausius showed how one could give up Carnot's assumption that no heat is lost in the operation of the Carnot cycle, while modifying Carnot's reductio proof of the theorem that a reversible heat engine attains the maximum possible efficiency. Carnot's proof then remains essentially valid with the correction that we have already discussed. It will not be possible here to do more than summarize the steps by which Clausius, with help from Kelvin, disentangled Carnot's insights from the caloric theory of heat and founded thermodynamics on a rigorous mathematical foundation. Clausius showed that heat is indeed interconvertible with work, but only in cyclic processes, with the maximum efficiency being achieved when those processes are reversible. Clausius and Kelvin were able to discover what had eluded Carnot, namely the precise mathematical formula for the maximum work that can be obtained from one cycle of an ideal heat engine operating between two fixed temperatures. More significantly for the future of modern physics, they established the existence of two properties of all bodies that deserve to be called functions of state, because they depend only on the present state of a system and not on the path by which the system acquired that state. Carnot's error was essentially to suppose that heat itself was such a function of state. Clausius first showed that not the heat, but the internal energy of the gas in a Carnot engine was a property of that kind. In any process, the change in the internal energy is equal to the heat added to the body minus the work done by the body on the external world. In any cyclical process, the change in internal energy is zero. Being a function of state was a necessary, though not a sufficient condition for internal energy to be conserved. Clausius next showed that a second quantity, which he was to name the entropy, was also a function of state. As Clausius discovered, the measure of the entropy added to a body when heat flows into it is simply the quantity of heat divided by the absolute temperature at which the process occurs. It follows at once that when heat flows directly from a hot body to a cold body, the net entropy of the two bodies and of the universe as a whole does not remain constant, but increases. In fact, entropy is conserved only in reversible processes, whereas in any process where heat flows directly from a hot body to a cold body, the entropy must increase. The second law of thermodynamics, as formulated by Clausius, asserts that the entropy of an isolated system either remains constant for ideal reversible processes or increases for real processes, but never decreases. A direct implication is that heat cannot flow spontaneously from a cold body to a hot body. And you will recognize the latter as the principle that we invoked to correct Carnot's flawed reductio proof. Looking backwards, one may see that Clausius's achievement is in a real sense a vindication of Carnot's insights regarding what goes on in heat engines. Carnot thought of heat at a higher temperature as somehow more energetic, more capable of doing work than heat at a lower temperature. Accordingly, to allow heat to pass directly from a hot body to a cold one is simply a waste of available energy, uncompensated by useful work. Since the measure of entropy change is heat lost or gained divided by temperature, we can now see that high temperature heat is low entropy heat and vice versa. The uncompensated flow of heat from hot to cold bodies is thus a spontaneous increase of entropy and a permanent loss of some portion of the usable energy in the universe. Not only did Carnot see that a fall of heat is necessary in order for heat to do work, he also believed that something absorbed from the furnace is passed undiminished to the refrigerator. He thought it was the heat, and he was wrong. But it does turn out that in a reversible engine, exactly the same amount of entropy that enters the engine at the furnace also leaves the engine at the refrigerator. Nearing the end. I have already reported the gloomy expectations that the second law of thermodynamics has inspired in some authors. In contrast to classical Newtonian mechanics, thermodynamics teaches that for any closed system and for the universe as a whole, the future is essentially different from the past and probably not for the better. Whether such thinking justifies a general mood of despondency, or rather a resolute determination to eat, drink, and be merry, is a question we might discuss after my talk. But to bring this talk to a timely end, I would like to point out three subtler implications of the discovery of entropy that may also prove worthy of further discussion. First, there is the interesting circumstance that Carnot's founding of thermodynamics was mixed up with an erroneous belief in the caloric theory of heat. Great as were the achievements of Kelvin and Clausius, I have little doubt that Carnot's insights regarding the fall of heat, the cycle, and reversibility were of far greater significance and originality than the theoretical advances they made possible. Now, it is always interesting when a great insight is entangled with a great error. But in this case, one could even make the case that the insight would have been impossible without the error. That is, that it was only because of the power in Carnot's mind of the analogy with the water wheel that he was able to see what no one had seen before, that the production of work by heat could only be understood in terms of a fall of heat in an essentially cyclical process and where maximum efficiency is achieved by permitting no uncompensated fall of heat. And yet, had Carnot been disabused too early of his false view that heat, like water, is a material substance that is preserved as it falls, the analogy with a water wheel could not have made such a powerful and fruitful impression. And one wonders, are there other cases in which a serious error has been the indispensable condition for a profound theoretical advance? Second, there is the perennial question of how much our understanding of the human things and of our place in the whole can be affected by the discoveries of modern science. In this case, that question takes an especially interesting form. I think there is little doubt that the existence and nature of entropy could not have been discovered apart from the modern scientific project. And it is well known that that project at its origin is closely associated with the goal of the mastery of nature for the enlargement of human power. But in this case, we find the peculiar circumstance that a major theoretical advance was achieved, and I would argue could only have been achieved, by intense reflection on a nitty-gritty problem of engineering, specifically how to improve the efficiency of a steam engine. Indeed, the science of thermodynamics was discovered not so much through contemplation of nature, but through study of machinery. The Carnot cycle is, after all, an idealization of the operation of a man-made engine, not of anything that is ever encountered in nature. The discovery of entropy, then, seems to be a case where not only modern science, but even modern technology as such, grimy, sooty, and oil-soaked, has produced key theoretical insights into the nature of the world and our place in it. This seems to me a point worth discussing. And finally, the subtlest and most interesting question concerns the theoretical status of the two laws of thermodynamics themselves. Of course, a perennial topic in the philosophy of science is what it means to call something a law of nature, and whether that grandiose phrase means anything more than a generalization from experience. Interestingly, Albert Einstein, who was typically skeptical of any physical theory's claim to absolute truth, wrote of the deep impression made upon him by classical thermodynamics, quote, "It is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown." As I mentioned earlier, the conservation of energy, the subject of the first law, seems to most people a more clear and intuitive idea than the increase of entropy, the subject of the second law. The former would appear to rest on the axiom, or perhaps the intuition, that a perpetual motion machine is impossible. That is, that work cannot be done without the expenditure of energy. This is but a more precise expression of the age-old conviction that there can be no science of nature. In fact, there can be no nature at all, unless nothing can come out of nothing. And that is a conviction that was shared by all the Greek philosophers, from the atomists to the idealists, and perhaps by every scientist since. But what is its basis? The scientific champions of the first law were inclined to invoke theological considerations. Joule, for example, declared that the grand agents of nature are by the Creator's fiat indestructible. And wherever mechanical force is expended, an exact equivalent of heat is always obtained. And Kelvin tells us he is certain that creative power alone can either call into existence or annihilate mechanical energy. Meanwhile, in the book of Exodus, when God wanted to attract the attention of Moses, he set in his path a bush that burned with fire but was not consumed. Only when Moses turned aside to see for himself why the bush burned but did not burn up, did God reveal his plan for the liberation of the children of Israel from slavery. Evidently, the qualities God was looking for in the leader of the Jewish people were scientific curiosity plus an intuitive grasp of the first law of thermodynamics. And yet, an intuition is not a proof, and the ultimate ground for our belief in the conservation of energy remains an enigma. Perhaps the only significant advance on this question was made in 1915 by Emmy Noether, the greatest woman mathematician in history. What she proved was that every conservation law is the consequence of a particular symmetry that is found in nature. The conservation of energy, in particular, is associated with symmetry or invariance of a certain dynamical function called the Lagrangian with respect to translation in time. Of course, Noether's theorem only shifts the question of the ground of energy conservation to the equally perplexing question, why are there such symmetries in nature? As for the second law of thermodynamics, it appears to rest on the intuition, or perhaps the axiom, that heat cannot spontaneously flow from a cold body to a hot body. That is, that it can be made to flow in that direction only if work is done on the system. I leave it to you to judge whether this rule is anything more than a generalization from experience. However, only a few years after Clausius coined the term entropy in 1865, the Austrian physicist Ludwig von Boltzmann began a program of research on the random molecular motions that underlie the large-scale phenomena studied by thermodynamics. What Boltzmann created was the science of statistical mechanics, one of whose principal results is a new and deeper understanding of the entropy law. According to Boltzmann, every macroscopic state of a body, for example, a volume of a gas at a given temperature, has available to it a multitude of possible microstates. In our example, the innumerable ways that mechanical energy can be distributed among the molecules of a gas in that state. Boltzmann showed that the entropy of a system is a function of the number of microstates available to a given macrostate. And as all microstates are presumed to be equally probable, the Boltzmann entropy turns out to be a function of the relative probability of the given macrostate. Translated into statistical mechanics, the second law of thermodynamics expresses the fact that over time, systems composed of many particles in random motion tend to evolve from less probable states to more probable states, and not vice versa. Sometimes the second law is informally said to involve a tendency toward greater disorder. But that is only because ordered states are, for the most part, highly improbable. Heat tends to flow from a hot body to a cold body simply because a collection of particles in random motion, yet with all the hotter, that is, faster moving particles, in one place, and all the colder or slower ones in another place, is highly unlikely to arise by chance, whereas a more or less uniform mixture of faster and slower molecules is much more likely. In the same way, a box of coins all facing heads up is likely, when shaken, to become a box with about half of the coins facing down. Further shaking is unlikely to reproduce the original improbable configuration with all coins heads up. If you find this intelligible, you have grasped the essence of the second law of thermodynamics as reinterpreted by Boltzmann. Hence my suggestion that, contrary to initial appearances, it is the first law of thermodynamics, the conservation of energy, that is ultimately mysterious as to its ground, whereas the second law, the increase of entropy, at least as clarified by Boltzmann, is the epitome of logic and common sense. Of course, the evolution of physical systems towards states of higher and higher entropy depends on the fact that underlying phenomena such as heat, there is an uncountable multitude of microscopic particles, each moving independently of the others, the whole ensemble governed entirely by chance. Thankfully, there are local pockets of the universe in which chance does not entirely rule, and temporarily at least, entropy may even increase. Finding and expanding those pockets is no doubt, for human beings, a large part of the pursuit of happiness. And now, lest I be accused of giving a talk with little or no relevance to political philosophy, let me close with a passage from the otherwise forgettable Thomas Pynchon short story, Entropy, whose main character in his youth read a little too much thermodynamics and is now tempted at age 54 to drift into the graceful decadence of an enervated fatalism. Quote, His had always been a vigorous Italian sort of pessimism. Like Machiavelli, he allowed the forces of virtù and fortuna to be about 50-50. But the equations now introduced a random factor, which pushed the odds to some unutterable and indeterminate ratio, which he found himself afraid to calculate. Thank you.
So the floor is open for questions now.
Thank you. Irreversible processes at work here. Please.
Thank you for a fascinating talk.
Thank you.
I'm wondering if the second law of thermodynamics makes it impossible in theory that we could have a universe that expands and then contracts again to have a second Big Bang that's similar to the first. That would seem to be a returning of the clock to the same state of, I guess you would say, higher energy. Is that right? And is it not possible that gravity could concentrate energy again in such a way as to reverse the process of dissipation?
Yeah, I think there's somewhat separate questions. That is to say, theories of whether the universe is expanding at an accelerated rate, as we now seem to believe, or slowing down and may someday contract, could certainly lead to periodic cycling between one form of energy and another. And there's nothing to stop parts of the world from witnessing a decrease of entropy as long as it's driven by work. Work has to be done. There's nothing about the universe that could ever correct for, if you put an ice cube on next to a pot of boiling water, that bit of entropy that is created there will never be destroyed. There's no going backwards in that sense. And so the universe as a whole has a never-ceasing increase of entropy. And that's true of any closed system. But an open system that has, for example, the Earth, you might wonder, well, what about life, which seems to evolve toward greater and greater complexity, and there are buildings where there was now wilderness. Isn't that order out of disorder? But that's because we're all parasitic on this vast energy source, the furnace of the sun, some very tiny portion of whose energy we manage to turn into useful work and to locally reduce entropy. But for the sun and earth together, the increase of entropy every minute is enormous. So, I mean, there are other questions related to the one that you ask that have to do with the possibility that the current configuration of the universe might someday arise again. At the end of the 19th century, Boltzmann's theory was very much in dispute with various thinkers. There were theories about so-called eternal recurrence that suggested that if you wait long enough with a random collection of molecules undergoing mechanical motion, that this system will get as close back to the original state as you please. And that appeared to run afoul of the claim of thermodynamics that the future is essentially different from the past. But I think that's a long story, but I think Boltzmann had good answers. He didn't persuade everybody, and he ended up killing himself, maybe partly because out of frustration. But I don't think that's a serious challenge to the increase of entropy. Mainly the problem is it would take an enormously long time, and so overwhelmingly the future is likely to be more probable and higher entropy and less ordered than the past. Please.
So it seems like the discovery, or at least the naming of entropy, required a change in perspective from thinking about forces like heat as bodies, as Carnot did, to thinking about the emergent properties of lots of little bodies. And that perspective certainly grew throughout the 19th century, and maybe you could say culminated in quantum theory and so forth. I wonder if We can't totally.
The perspective you're talking about is the molecular microscopic perspective?
Sort of a continued move from thinking about forces as conserved wholes to thinking of them as epiphenomena, smaller.
It's a complicated question, and I don't think it's quite as you describe, because you have on the one hand the discovery of entropy and the realization that heat is not something conserved, and you have the second law having distinguishing the future from the past, and therefore suggesting that there's a history or the future is getting worse. But and then on the other hand, you have this switch from the first field I was describing, thermodynamics, which describes large-scale bodies such as we experience, and it characterizes them in terms that are familiar to us: temperature, pressure, volume, and the statistical theory, which tries to look at the underlying molecular events going on. So it doesn't seem to me that, first of all, thermodynamics isn't replaced by statistical mechanics, it's supplemented it by it. It's still the case that we need a theory of what's going on at the level of macroscopic experiments. We just want to correlate that with this molecular description. But it doesn't seem to me that the pessimism that I've described is essentially dependent on that molecular turn that occurs, with the rise of the kinetic theory of gas and Boltzmann statistical mechanics. Does that make sense? I mean, there were certainly thinkers long before entropy was discovered who believed in atoms and thought that underlying, that a gas is a collection of little particles in random motion. So it's an interesting and complicated question. Right behind?
Perhaps just as an addendum to Professor Pengel's question. So you're saying that there could be a big crunch, but the entropy would still be higher in that state? Or you're just saying it's extremely likely that, or extremely unlikely that there would be a big crunch?
Well, say more about why the so-called big crunch would be a low entropy state.
Oh, no, I said high. I thought you were saying that,
Or why?
I thought you were saying that if there were a big crunch, the entropy would still have to be higher. Is that possible? Higher than
Well, I am not a cosmologist, and I don't really know the physics of what would happen in a big crunch, but I think, to the best of my knowledge, it's not the case that any of these cosmological theories involves a suggestion that the second law of thermodynamics will be reversed, or that entropy will be reduced.
I guess I just always interpreted those theories as saying things would return to the way they were. And if entropy were higher, they wouldn't really return to the way they were. So that's
Well, by the way they were, you mean our world will be restored, or
well, I don't know really. I'm curious about that contradiction.
everything will work backwards, you mean? Is that the idea?
No, that everything would start over the way it was. I'm confused about how that can square with entropy still higher. So then the state is not as it used to be. So it's a theoretical contradiction that I don't understand.
Yeah, I'm really not competent to comment on this. I'm stuck in the 19th century or even earlier.
I mean, I keep thinking about how you talked about entropy as pistons going up and down, and turning wheels, and then of course in the public understanding of it, they immediately lead, and some scientists too, they lead to the entire world, the Big Bang, beginning of life, the meaning of life.
Right.
It seems like it's like the beginning of a misunderstanding of concepts in science. I'm looking ahead toward relativity, or Heisenberg uncertainty principle, quantum, how those things have been so misunderstood by the public, or how maybe one segment of the public receives them because they favor some pre-existing theory that they have. I'm wondering if
Well, sure.
I think entropy may have just been received by pessimistic people as, oh, this is perfect for me.
I mean, I could see that in the case of relativity, you know, the unfortunate choice of the word relativity for the theory, or some ways unfortunate. You know, Minkowski joked that it really should be called the theory of the absolute world, not the theory of relativity. And who knows, maybe it would have led all kinds of optimistic people to think, oh, it's not all relative then. So I could see that there, but it's not entirely clear to me that what you're referring to is a misinterpretation of the entropy principle. It begins with Kelvin in 1852 in that passage that I read. A couple of years later, Helmholtz, the no slouch himself, completely endorses that interpretation, that the universe is headed toward room temperature, that eventually all heat differences of temperature will have been replaced by an equilibrium and no further work will be done. The world that we see around ourselves will be impossible, or our surroundings will be in a state that is uninhabitable to human beings. Maybe the emotional reaction to that is not in itself built into the theory, but I don't see any essential distortion there the way you're describing.
Well, I mean, Kelvin could have spun it as saying, that's not going to happen for 10 billion years.
Oh, he did. Yeah, and actually,
The public, I don't think, picks up on that. I mean, it really has no relevance with their own personal 70-year-old life, you know. So, I mean, they could have, he chose to
I see.
emphasize one aspect versus another.
You're saying it's so far off that the heat death that, yeah, it's true that in the late 19th century there were paintings of people kind of shivering and icicles. Yeah, and so you might ask, well, who thought we were going to be around forever? Why should we be worried about what happens billions of years from now? But I don't know. I think, yeah, you could console yourself in that way. On the other hand, the thought that there's no possible way that what we are and what we care about could be a permanent feature of our world is a dark thought, isn't it? And to have discovered that, Helmholtz was very impressed by Kelvin and said it's just amazing that he looked at a little formula involving pressure, temperature, and volume and describing the workings of little steam engines and drew from it conclusions about the ultimate eternal rest of the universe. That was he said, we really have to admire that kind of wit. And maybe wit's the wrong word, but please.
Whenever I've read about entropy before, it's always been described as an increase in disorganization.
Yes.
Yet you didn't use that phrase, and I wonder if that phrase is consistent with your understanding of classical thermodynamics.
Yeah, I had one parenthetic remark about how it's normally spoken of as a rule of a motion from order to disorder, whereas I thought it was more precise and correct, following Boltzmann, to say that the universe tends to move from improbable states of organization to probable ones. And the reason I prefer that to order and disorder is because order and disorder are to some extent subjective, and there might be states that to us look highly disordered, but are very low entropy states. And on the other hand, there might be states to us that look highly ordered, like the mirror surface of a beautiful woodland pond. That is a very high entropy state, whereas a huge jumble of churning water molecules of many different elevations, which looks completely random, is on the contrary a very difficult state to achieve by the laws of thermodynamics, and therefore is a low entropy state. So it seems to me safer to say the conditions that we value, like having tall buildings that are not crumbled heaps of rubble, are they happen to be highly ordered, but the reason they don't arise spontaneously is because they're improbable, not because they're ordered. Does that make sense?
Yes, it also makes sense to
No doubt, right. Any other questions?
Well, thank you very much.
My pleasure.